Okay, we're going to look at the mixed practice problems from Classwork 5.3 on angle bisectors. Okay, so the first problem says calculate the distance between the line and the point shown on the coordinate plane below. So we're given the point and the line. You have to remember that distance is defined as the shortest distance, which is given by the perpendicular line segment. So I want to find some line segment through this line that goes to this point, and I want to make sure that it's perpendicular. And just looking at the graph, it looks like this given point will be it, but we need to make sure and actually confirm. So to do this, we can calculate the slope of this line. The rise over run is 1/3, meaning that a perpendicular slope would be -3/1. And using that perpendicular slope, I can start at my point, down 3/1, down 3/1. We see that in fact it is this coordinate 6, 2. So we know that this segment is the shortest distance between the point and the line. Now we can use that to calculate the length of the segment using either the distance formula or the Pythagorean theorem. And we can see that there's a difference in the y-coordinates of 6, a difference in the x-coordinates of 2. So we would say that the distance squared is equal to 6 squared plus 2 squared, or the distance squared is equal to 36 plus 4. Distance squared is 40, so the distance is given by the square root of 40. Okay. If we wanted to simplify this radical, we could also write this as d is equal to the square root of 4 times the square root of 10, or the distance is 2 square root 10. And that could be turned into a decimal approximation using a calculator as well. All right, problem number 2. We want to calculate again the distance between a point and a line. Okay, so we want to model this a little bit. I'm going to draw a coordinate plane. And the point 3, 5 might be somewhere up here. And the line y equals 2x minus 11. So that is going to have a y-intercept of minus 11. And it's going to have a slope of 2. So I don't know exactly where that's going to go, but I can visualize it like this. And that helps me because I know I want to find the distance, the shortest distance given by this perpendicular segment to the line between that point and the line. So I need to know what coordinate does this perpendicular segment intersect at. And so what I'm going to do is I'm going to find the perpendicular line through this point. I need the perpendicular line through that point, perpendicular to this line. So first I'm going to take my slope. I'm going to get the perpendicular slope. So 2 is perpendicular to -1/2. Then I'm going to use point slope form, and I'm going to take my slope, or my point here. I'll say y minus 5 is equal to -1/2 using this perpendicular slope, x minus 3. And now I need to know, where do those two lines intersect? What are the coordinates of that point? So I can build a system of equations. If I distribute and change to slope-intercept form, I'll get y minus 5 is -1/2 x. -1/2 times -3 is positive 1.5. Add 5 to both sides of my equation, and I get y equals -1/2 x plus 6.5. Quickly check to make sure that's right. 1/2 of 3, 1.5, add 5. Looks good. So now I want to know, where does this line intersect with the original line? Where is that intersection point here? So what we're going to do is we can set them equal to each other. -1/2 x plus 6.5 equals 2x minus 11. I'll add 11 to both sides, so I'll get 17.5. And then I'll add 1/2 x to both sides equals 2.5x. I'm going to get x equals 17.5 divided by 2.5. Okay. Now I can see that that's related to 175 divided by 25. I know 25 goes into 100 4 times and into 75 3 times, so I know x must equal 7. So that's the x-coordinate of our point of intersection. Next, I want to find the y-coordinate, so I'll substitute that back into one of the equations. 2 times 7 is 14, minus 11, so my y-coordinate must be 3. So the coordinates are 7, 3. And now I simply need to just find the distance between this point 3,5 and this point 7, 3. So I could use the distance formula, but I always prefer to just use Pythag because that is the distance formula. And so the difference in my x-coordinates is 4. The distance in my y-coordinates is 2. And so if I wanted to find that distance between these two coordinates, I can use Pythag, and I can say 2 squared plus 4 squared is d squared, 20 is d squared, and d is the square root of 20. Again, if I wanted to, I could simplify this. D is the square root of 4 times the square root of 5, or d is 2 square root 5. Okay, you can find the decimal approximation if you prefer as well. All right, moving on to problem number 3. It says point J lies on the perpendicular bisector, I'm going to highlight this keyword, of some segment AB with endpoints of A, 1, 5, and B, 11, 5. Okay, so I'm going to draw this out. I immediately note that these y-coordinates are identical, so this is a horizontal line segment AB. So I'm going to model my givens here. A at 1, 5. B at 11, 5. And then I have some perpendicular bisector of AB. So I'm going to draw a perpendicular bisector such that these two segments are congruent. It is perpendicular, and point J is somewhere on that segment. So this could be J, this could be J, this could be. Any point could be point J. Our goal is to find the coordinates of J, given that we know JB is 13, and the slope of JB is negative. So wherever I put J, I need to find a point where JB will have a negative slope. And so if I think about this, if I put a J down here, well, that gives JB a positive slope. But if I put J above segment AB, well, then JB will have a negative slope. If I know JB is 13, I can fill this in. And now I notice that I have a right triangle. Well, I know the hypotenuse is 13, and because AB is a horizontal segment, I can find the middle of the x's. The middle of 1 and 11 is 1 plus 11 over 2, which gives us 6. So this midpoint here is at 6, 5, and that tells me that the length of this triangle, the leg of this triangle, is the difference between 11 and 6, which is 5 units. So essentially, I have this right triangle with B, J, and some midpoint coordinate. JB is 13. This leg is 5. I can use Pythag, again, to find the length of this side. And I'll just call that x for a second. So I'll say x squared plus 5 squared is 13 squared. Well, this means that x squared plus 25 is 169, or x squared is 144. Square rooting both sides gives x is equal to 12, so the length of this side must be 12. Going back to our diagram, I put 12, and if I know the coordinates of this midpoint here, which I'll call M, was 6, 5, and J is on this perpendicular bisector, which must be a vertical segment because AB was horizontal. So the bisector must be vertical. That means I just can add 12 to the y-coordinate of M, and my coordinates of J are going to be 6, 17. Problem number 4, it says consider point P, given the coordinates -1, 3. Find point Q, so I'm looking for some other point Q, for which the line 2x plus y equals 5 serves as the perpendicular bisector of segment PQ. Okay, let's get a diagram going. Point P is at -1, 3. And I'm trying to find some point Q for this, where this line is the perpendicular bisector. So I'm going to turn this into slope-intercept form, y equals negative 2x plus 5. I'm going to try to model this. So 5, somewhere up here, and negative 2x means we have a slope of negative 2, so it looks something like this. And so now I'm looking for what is the coordinates of point Q somewhere up here such that this line is the perpendicular bisector. So that means that perpendicular bisector of PQ is this line. Okay. So my first order of business is I would like to find an equation for the line PQ. So if I start, I can say y must be equal to, we're going to use this slope and take a perpendicular slope. So the perpendicular slope to negative 2 is 1/2. So y is equal to 1/2. I'm actually going to use my point slope form. Y minus 3 equals 1/2 x minus negative 1 or plus 1. So that's the equation of this line, the whole line of PQ. And I want this because if I know the equation of this line and I set it equal to this line, I can find this point of intersection between line PQ, I should say, and this other line. So I'm going to turn this into slope-intercept form, distributing y minus 3 is equal to 1/2 x plus 1/2, or y is equal to 1/2 x plus 3.5. I'm going to set that equal to my other line to find where they intersect. So I can say negative 2x plus 5 equals 1/2 x plus 3.5. Add 2x to both sides, getting 2.5x. Subtract 3.5 from both sides, and I get 1.5. Divide both sides by 2.5, and I have 1.5 over 2.5 is equal to x. Now, if I want to reduce this, well, I could look at this as being the fraction 3 over 2 over the fraction 5 over 2. And if I divide one fraction by another, I can also treat this as 3/2 multiplied by the reciprocal, by 2 over 5. The 2's cancel, giving me x is equal to 3 over 5. Now that x coordinate belongs to the point of intersection, 3 over 5. And so now I need to find the y coordinate of that point of intersection. So I can substitute that back in to either equation. And so I'm just going to pick this one. So I get y equals negative 2 times 3/5 plus 5. Negative 2 times 3 is negative 6 over 5. And I'm going to want a common denominator, so I'm going to turn my 5 into 25/5. Combining, I get y is equal to 19 over 5. So that is the coordinate where these two lines intersect. And for this point Q to exist on the other side of that line such that this line is the perpendicular bisector, that means that my change in y and change in x must be the same on this side as it is on this side. And that means, let me get this out of the way. That if I go from the point P at negative 1, 3 to this point of intersection, 3 over 5, comma 19 over 5, well, point Q has to be somewhere such that this x change and y change is also the same as this x change and y change. So these segments are congruent, these would be congruent, because our whole goal is for this to lie on the perpendicular bisector, making this the midpoint, and these also must be congruent. Okay, this coordinate, the midpoint here, is in terms of fifths. So I'm going to convert p into fifths, so negative 5 over 5, comma 15 over 5, so that it's easy to see my change in x. So to go from negative 5/5 to 3/5, I would need to add 8/5. So this change is 8/5. in the x direction. The change in y is from 15/5 to 19/5, so the change is 4/5 in the y direction. And so I'm going to repeat that from m to q. So I'm going to add 8/5, this length, to 3/5, that coordinate, to find my x-coordinate of q. And so 8/5 plus 3/5 is 11/5. So the coordinates of q are 11/5 for my x. Then I'm going to use the same idea with the y-coordinate. So 4/5 is my change in y from p to m, leading me to my coordinate of 19/5. So I need to add this to 19/5 to get from m to q. And so if I say 19/5 plus 4/5, I'm going to get 23/5. So 23/5 must be my coordinate for q, or my y-coordinate for q. If I really wanted to, I could convert those into decimals. So that is 2 1/5, or 2.2. 23/5 is 4 3/5, or 4.6. So either of those are acceptable answers for the coordinates of point Q, such that this line is the perpendicular bisector of PQ. Okay, and then finally we have this proof. So FC is the perpendicular bisector of AB. So I'm going to mark that these are congruent and a right angle. Then we see that FE is the perpendicular bisector of BD. So I'll mark these congruent and that that's a right angle. I'm trying to prove AF is congruent to FD. So I'm trying to prove AF here congruent to FD. Okay. So this one we can think about, but what I'm going to realize is by the perpendicular bisector theorem, I know that, for example, this point F is equidistant from point B and point D. So if I were to draw in a segment BF, I could say BF is congruent to FD. I'll make a note of that. BF congruent to FD. Then I can also say this point F is equidistant from A as it is to B, because it is also the perpendicular bisector of AB. So this is also equal to this. So I can say FA is congruent to FB. So if I know that FD is congruent to FB and FB is congruent to FA, well then I can say the thing I want to prove. AF is congruent to FD. So now it's a matter of structuring it into a proof. Statements, reason, start with my givens. Okay. Then I can say segment BF. We're going to just say construct BF. And we'll just say that's construction. Now I can say BF congruent to FD by the perpendicular bisector theorem. If a point lies on the perpendicular bisector, it is equidistant from the endpoints. I can also say that FA is congruent to FB by the perpendicular bisector theorem. And that's it. Now I can just say BF is congruent to FD, and then FB, which is the same as BF, just written differently, is congruent to FA. So by the transitive property, I know that FA must be congruent to FD. Actually, it maybe is more clear if I write this one again as BF instead of FB. BF. So the transitive tells us these are all the same. We have proved what we want to prove, so we can say QED smiley face. Very good.